See my slides?
Yeah, the machine learning.
Yep, great. Okay, so
Sweet.
I'll try and keep it relatively brief. I'm going to be describing a code called PySINDy that we've been using for what's called system identification, which is a general method that a lot of folks use in science, but be sort of focusing on the plasma physics, heliophysics side of things at the end here. And yeah, we're sort of in the process of adding this to PyHC, and hopefully researchers from that field can find this of interest and of use. But yeah, this talk will be sort of on general system identification in science. So if you're interested in the paper describing code, check this out. Our code is on GitHub, and we also have like 10 YouTube lectures that show you how to use various aspects of the code. This is all done at the University of Washington Data-Driven Dynamics Lab. So that's Steve Brunton and Nathan Kootz's lab here. And I did my PhD there. I'm now at the University of Maryland doing a postdoc. So I'll be describing what system identification is, why it's a useful tool, what sparse system identification is, and then I'll be sort of doing a rapid fire advances in the last few years that really made these more useful tools. And all these advances we put into the PySINDy code now. So our hope is folks can basically come with interesting data sets and very quickly find models and interesting dynamics for that data. And then I'll sort of briefly describe PySINDy, and if there's a little time at the end, just shows 2 quick examples. So what is system identification? This is the process of identifying dynamical models directly from data. So there's it breaks into roughly 2 branches. One are these physics-based inductive models. You might use something like this for robotics. So this might be a coupled system of differential equations that you want to extract from some data set and then use that to extrapolate to new initial conditions, new processes, etc. And then the other side of the coin is are these statistical models that you might use for something like self-driving cars. So these sorts of models have no idea what roads are, what people are. All it has is probabilistic models and probabilities for certain things appearing in the road. So you train these things with probabilistic models, probabilistic rules, and based on that, it decides what to do. And both are useful, obviously, but I'll be focusing on the former today, these equations-based models that you can extract from data. And I should say, I want to keep this relatively informal, so please interrupt with any questions at any point. Okay, so one way you can extract models from data is you just imagine you have some data set. Of course, we're going to use Lorenz because it's easy to show and understand. So you imagine you have some simulation or experimental data. It's evolving according to some underlying governing equations for these 3 variables that we're going to pretend we don't know right now. And then you just imagine you take some measurements here. You compile that data into this big data matrix X dot. So here we have measurements of each of the X, Y, Z and their time derivatives. We arrange that into some matrix. And then we do something relatively straightforward. We build a candidate library of possible terms that could describe how that data evolves in time. And then this coefficient matrix just chooses how strong are each of these terms in those evolution equations. So we're just building a big set of possible models that could describe how the data evolves in time. And then we're going to use simple regression to basically find the model that best describes how the data is evolving in time. So regular linear regression is easy. One way to phrase it is you just do, you ask for the set of coefficients that minimizes the difference between your measurements and the left-hand side and the right-hand side, which is this, this model you're trying to fit the data. It turns out, for reasons I'll show in the next slide, this tends to not work very well. The advantage is this is a nice convex thing that has an analytic solution, but typically folks will add what's called a sparsity prior. So this is just an extra term in this optimization problem that tries to basically minimize as many of these coefficients as possible. And that's really nice because that tends to give you sort of sparse parsimonious models rather than these very dense models I'll show in the next slide. And that tends to really help with these things. So for instance, Lorenz actually, we've built a candidate library here of up to 5th order polynomials in X, Y, and Z. But Lorenz actually has relatively low order not linearities and non-linearities here. So actually we do want to promote sparsity when we fit to data like this. So you might add what's this L1 norm here to do that. This is still convex. Turns out it tends to work even better if you add what's called the L0 norm there. And this was the main sort of innovation of my old advisor Steve Brunton and Nathan Kutz's their paper in 2016. And basically the idea is now this sparsity prior, if you don't know what the L0 norm is, it literally just counts the number of non-zero terms in the model. And then this parameter here can be used to basically truncate all the non-zero coefficients below some threshold down to 0. So that was a lot of words describing basically the picture here. So if you solve this optimization problem for Lorenz, you might get a set of coefficients that looks like this. So let's look at the first equation. We get about a -10 on the X term and a +10 on the Y term. And indeed, that's exactly what we'd expect for Lorenz, up to some numerical errors, of course, because you're sampling this at some finite discretization. But all the other terms in the model are nicely truncated, not just to small numbers, but exactly to 0, because we've used this L0 norm here. And similarly, you can go through the other equations too. So just to show you what this looks like in PySINDy, sorry for the huge text here. But basically, what you can do with PySINDy is just define some variables saying what the names of your variables are. So I've preloaded some Lorenz data in here. We say the names of the variables are X, Y, and Z. We define some optimizer for the SINDy regression. In this case, we're using this lambda with a 0. So we're just going to do linear regression first. And then I'll turn on a non-zero lambda and we'll do the L0 regression. So first, lambda equals 0. We just say, please make a SINDy model with these feature names, with this optimizer. And then we just fit to some preloaded Lorenz training data with some sampling time step here. And when we print out the model, you can see it basically gets the right model. It's got a -10 on this X term, a +10 on this Y term. And similarly, you can go through the other equations. But you'll notice there are these sort of spurious small terms that are incorrect in this model. And this is because it's sort of overfitting to the data. And these sort of spurious terms will get worse and worse as the noise increases. I think this is on like clean data with a pretty nice sampling rate, and still it picks up these spurious terms. So anyways, you can repeat this, but now we're going to set some finite lambda in this L0 norm optimization. And now you can see it gets the Lorenz terms exactly right, again, up to some numerical precision in the coefficients. So I'll just take a pause there. I need water, so.
Can I take this opportunity to ask a question?
Please.
Yeah, seeing the sparse regression optimizer here, do you have other ones, and were you going to talk about them later in the talk? Should I just wait, or?
Yeah, so I wasn't going to discuss them because the optimization side is a little more advanced. But we do have a lot of different optimizers. We have at least 5 or 6 that are inbuilt in the PySINDy code. And then all of this is built on top of sklearn. So sklearn has a lot of optimizers for the L1 problem, since it only does the convex optimization. But
Gotcha.
sklearn has all the inbuilt like elastic net and lasso and these things.
Nice. And just real quick, because this actually like obviously did pretty well in modeling the Lorenz there. Like how much data did you feed into it? Like was it, you know, just a day's worth of data, years? How much?
Yeah, hard to say for Lorenz. We use this sort of dimensionalized data, but I'm not sure for this. We probably sampled this at a pretty high rate, but I'll talk about in a couple slides. We have a number of advances we put in that let you use very little data. So I'll sort of be showing less and less resolved data as we go along here, and hopefully that can give you a sense.
Cool. Thank you.
Yeah. Yeah, so here's my rapid fire advances. So the first thing you might try and do is just expand this SINDy method for identifying PDEs from data. So this is a simple example of what you might do. So now you have some 2D flow field like the von Karman street. Again, you collect some data as a function of at some time snapshots. And let's say you pick out the point measurements of the vorticity and the two components of the velocity. And what you're trying to build is a system of PDEs, or in this case, a 1D system of PDEs for the vorticity. And all we need to do is take our candidate library from before and just add terms that now contain spatial derivatives of the data. So in this case, we take the vorticity, two components of the velocity field, and sort of products of them and their spatial derivatives up to second order. And once again, you solve this optimization problem, and they nicely show in this paper they can get this simple 2D flow from this data. And we sort of, if we have time, I'll show a quick 3D example with the PySINDy code. Other things you might want to do is incorporate physical priors, physical constraints into system identification. A big one for fluid flows is that the convective nonlinearity in the Navier-Stokes equations is almost always globally energy preserving. So this is what this equation is encoding. And this means that this nonlinearity has a skew symmetric structure. And so we would actually like to build that in a priori so that our models just immediately satisfy that property. So you can actually do this. It turns out this improves accuracy and stability, and you can just alter that optimization problem, add a Lagrange multiplier, and then put in your constraint on the nonlinearity here. Turns out skew symmetric quadratic nonlinearities are common, and in particular common in MHD. So I'll just flag that here. We actually sort of took this and ran with it and built what's called trapping SINDy. And this gives you actually globally stable data-driven models by construction. So we noticed that the skew symmetry constraint gives you more stable, accurate data-driven models, but it doesn't guarantee you have globally stable models. But there's we found this paper by Schlegel and Noack that gives conditions for global stability for these quadratic data-driven models you can get from the data. And so we just built that directly into the objective function, solve some new non-convex optimization problem, and then we can actually, for these like 2D flows, we can actually build globally stable models that are provably stable for any new initial condition. So if you take some, you have some nice fluid flow over the cylinder, and you suddenly like hit it with a delta perturbation or some crazy initial condition, it will still give you sensible results, and it won't just blow up or something weird. And I'll just briefly show that and speed this up. So I'm comparing the ground truth on the top, our model on the bottom, You can see it gets the transient timing right. It's then going to overshoot for a second, screw up the wake, and then it'll recover from the overshoot and get the long-term shedding correct. Meanwhile, this is the sort of analytic POD Galerkin model that was sort of the state of the art in 2003. And it sort of gets the transient timing pretty wrong. And then you'll see it never really gets the weight correct. It's got some shimmering and numerical artifacts. So not only can we sort of build these models purely from data, this actually uses very highly sampled resolution simulation data and high order derivatives. But we can get it directly from the data and have this provably globally stable models. So we put that into the code and you can play around with it. Another big thing are another person in our lab, Urban Fossell, has a recent paper on model ensembles. This is a really fancy way of saying do SINDy, but do it basically subsample your data and make like 100 or 1,000 models, and then use that to actually give you statistics on the coefficients that you identify. So this is a simple hair link system. This is like a classic predator-prey system in the dynamics field. And what he does is, builds like 100 models, identifies distribution of the types of coefficients that occur in this simple library of terms, and then can use that to actually compute inclusion probabilities for each of these dynamical terms in the final equations. So in this case, these two pass some threshold, and these two pass some threshold, and then you can actually generate forecasts that are quite accurate and actually give like 95% error bounds because you have access to these distributions of the coefficients that appear in these models. So that's sort of an old technique. Actually, it's sort of just basically bootstrapping, but we've built it into the code, and it really can help with robustness to noise and giving you uncertainty quantification. One last thing hopefully last thing I'm going to flag is a big innovation for reducing the sensitivity of these methods to noise. And the trick is basically to identify the weak formulation, otherwise known as the integral formulation of PDE or ODE. And that really helps in a way that I'll describe here. So we're going to again consider the SINDy problem, which is you have some spatiotemporal field, which is evolving according to some underlying governing equations that you want to discover. And now what we're going to do is just basically multiply both sides of this equation by some spatiotemporal weights, Wx of t, and then integrate over some subdomains, omega k. What is nice about this is we can choose these to be smooth weights on these compact subdomains, and then we can actually take all these derivatives, there might be derivatives on here as well, and just integrate by parts and take these derivatives which were originally on noisy data and put those derivatives onto these smooth weights W that you can actually choose. And so basically you avoid amplifying all the noise from computing derivatives on noisy data. And moreover, you can eliminate the surface term when you do the integration by parts by choosing W to vanish on the boundary of these domains. So this is a really nice trick that avoids one big problem we see, which is if you have noisy data and you try and differentiate it, you just amplify things and the problem gets worse. It turns out if you do this and basically stack a bunch of these subdomain integrals together, you once again get a problem that looks exactly like the original SINDy problem. You have some matrix of time derivatives equals some candidate library times some coefficients. So once again, we can basically take all the optimizers that are already implemented into PySINDy and immediately use them for this weak form problem. All we need to do is in the back end, we compute all these integrals and do all this shaping. And just to drive home just how useful it is, I've taken a simulation of Lorenz added white noise with 0 mean and 10% noise. Here, 10% of the average absolute value of the training data. And that maybe that's not so intuitive, but you can basically see I plotted it here, and we basically sampled a noise data point and put it on every single point in the training data. So you can still kind of tell it's Lorenz, but it's got some crazy variation here. And basically, regular SINDy can't handle this at all. So here I'm plotting the candidate terms for a quadratic library for Lorenz. And then I'm plotting the coefficient values for the x dot equation, y dot equation, and z dot equation. So if you look at the weak form results for the x dot equation, you can see it's still getting a -10 on the x and a +10 on the y term. So the weak form is exactly getting the equations right, despite all the noise we've added, and even has pretty small error bars. So the error bars are because we fit like 100 models and then looked at the variance. But you can see regular SINDy actually totally gets everything wrong. It can't handle this level of noise and just gives spurious results for basically all the coefficients. So takeaway is the weak formulation really, really helps with significant noise. So what is PySINDy? We've basically, this is a Python code built by the lab at UW. We originally only had this like very limited traditional SINDy method. We've since put in all these advances I just briefly described. And why should you use it? It's open source, high quality. We have tons and tons of examples, fully reproduce a number of these papers in the literature. We have a number of active developers. It's easy to use. And as I mentioned, we put in a lot of this advanced functionality. So you can really do interesting things with it now. It can actually identify extremely general equations from data at this point. It can do arbitrary spatial dimension, arbitrarily large systems of partial differential equations, including with fully spatial temporal control inputs. So this is like an extremely general partial differential algebraic equation with control. So I don't know if anyone has gotten that ambitious with it yet, but yeah, it's really, really general. And we actually have some folks working on putting integral differential equations in here. So it'll be even more general soon. Just to flag some possible applications in plasma physics. So there's been a lot of system ID work in this field. Most of it has been done either with linear control models or fully black box neural networks. But it would be nice to have sort of a transition between the two that are interpretable nonlinear ROMs. And basically no one has started using these advances in the plasma physics field yet. But the PySINDy tool is out there, so we think there's lots of opportunities. And I've just flagged some interesting ones down here. And we can, if anyone has questions, I'm happy to discuss them in more detail. So just to summarize, system ID is useful in a lot of different scientific fields. I've described what sparse system identification is and shown you some further advancements that really help. And we put all these new advances into the PySINDy code. And just checking, you can see my my full browser, I hope. So you can now see my Jupyter notebook. Okay, cool. Yeah, so I just wanted to show some really basic usage directly in the PySINDy code. So we have these Jupyter notebooks, and again, we'll just look at the Lorenz system. It's really very few lines. So we generate some data, we build a SINDy model, we put that data into model.fit with the time step, and then we print the result. So that's it. It's really, really nice. And then basically you can assess the results on a test trajectory. So here we basically make some testing data. We do model.predict to predict the x dot on that testing data. And this is what it looks like. So it basically perfectly matches the time derivative of the testing data, gets it just right. And then you can actually simulate that new model with the initial condition of the testing data and check, does it fit x0, x1, x2, not just x0 dot, x1 dot, x2 dot. And when you do that, it also does a pretty good job, but inevitably it misses a lobe switching. And that's just because Lorenz is a chaotic system. So it sort of starts on the right track, but then it'll miss a lobe switch and lobe switch at a slightly off time. And that's despite getting the coefficients very, very close. So this is just a fundamental part of chaos. So that's sort of the simple use case here. We just took some Lorenz data, fit it very easily, predicted the new dx/dt and the new trajectory, and can compare it to some testing data. To show you can do something a little bit more complicated, I'll just briefly describe this, the PDE functionality for a 3D reaction diffusion system. So this is a set of two PDEs with some diffusive term on these in these PDEs, and then some linear and cubic terms. And this is in full 3D space, so we can basically this is not much harder to use in the PySyndy code. You just have to do some shaping. I'm going to skip this part because this is just generating the training data for this. So if we skip that, this is what the initial condition looks like in the midplane. So it's got this sort of interesting swirly structure. And the main things you need to do are just build a spatial grid, define some functions that you want to put into your SINDy library. So I apologize for the lambdas, but so this might be hard to read for some folks, but basically this is saying I want linear functions, I want cubic functions, and I want mixed cubic functions. So that's all I'm saying is make me a SINDy library with linear and cubic functions. I define the names of those functions, and then I just make a specific library saying I want these functions. I want spatial derivatives up to second order in every direction. So in X, Y, and Z and the mixed terms. Here is the spatial grid defining the 3D space that I'm looking at. I might want to include a bias term. Here I'm specifying that the spatial grid is actually uniform in all directions. And here I'm specifying that the grid is actually periodic, so I wanted to respect that fact. And once again, so all I did is I made some library that is telling you how to generate this PDE library. I choose some optimizer that I want. Don't think about this too much. This is sort of arbitrary. And then again, we just build a SINDy model with the library and the optimizer that we want, and we fit the training data that we've generated. And we basically get the right thing. It's got some larger numerical errors on these terms, but that's mostly because the data here is pretty low resolution. So you can see here it's pretty low resolved in each of the spatial directions. But nonetheless, it's pretty straightforward to generate these 3D PDE systems. So I'll just stop there, and if any folks have questions about the notebooks or want to see some examples, just let me know.
If no one else has a question. Oh wait, actually, here, let me look in the chat. I've got a question here, I think. I'm just gonna read it. Could you say some words about the differences of PySyndy versus PDE find and deep symbolic optimization?
Yeah, so PySyndy basically does PDE find plus much more at this point. So for folks that don't know, PDE find is just a euphemism for do SINDy for PDEs. So not only does PySyndy do that, but it actually can do fully weak formulation of the PDEs, and it's way more robust than the original PDE find. you can actually combine all these methods I've described. So you can actually do like ensembling with the weak formulation on an n-dimensional PDE. So you can build like 1,000 PDE models and then do all this checking the statistics on the coefficients. So we've totally absorbed all the PDE fine stuff. And then deep symbolic optimization, I'm not super familiar, frankly. So I don't want to speak too much of this, but if you have a more pointed question about it, like some technical thing, I might be able to answer.
Thank you. If you don't have a follow-up question to that, I'll take my turn to ask a question. So looking at this code here in the notebook to train the models on the data, I'm not seeing a whole lot of places where you have to manually fiddle with like hyperparameters for the algorithm. And I'm not really seeing any guess and check kind of things there. Did I miss any of that, or does this code really just twiddle all the hyperparameters for you until you have a good model?
No, so that's something we probably should put in at some point. I somewhat ignored the hyperparameter tuning here. So one, there's somewhat of a tuning to be done by choosing the library that you want to look at. Sort of we're allowing, we've built these libraries that are sort of super flexible and you can make very large very easily. And our hope is to parallelize the code so you can actually like run these very fast. But then there's also hyperparameters in the optimizer, which I've sort of glossed over. One is the lambda in the sparsity prior. This is this threshold here.
That could be like any number.
That can be any number. And then these are not so much hyperparameters, but some of the other optimizers have more hyperparameters. So indeed, based on your data, what you're looking for, you might want to tune these a bit. And we don't have any automation there. One, because we haven't done it yet, but two, I think it might be confusing to users if it did this tuning automatically. Because there's like different ways you might want to choose the sort of optimal threshold, for instance. Yeah, it sort of depends on how sparse do you want the model, like do you want the lowest error model, do you want the like lowest error subject to some sparsity threshold. So there's different ways you can choose. So we'd have to think about that a bit more.
Nice, thank you. One more question from the chat that was similar to another question I had, so I'll mix it into mine, is they're saying, you can also use a mix of autoencoders to solve dynamical equations in latent space. And obviously autoencoders are a kind of neural net, which you haven't mentioned here yet. Does this code dabble in neural nets or autoencoders, or do you just stick in the like kind of linear equation space?
So yeah, currently we don't dabble, but this is something we're interested in. Maybe I'll just pull up. One of the people in the lab has a recent paper. That basically does an interesting combination of these, where they imagine you have something like Lorenz, but you only have measurements of, let's say, the first variable, like x dot. And then what they do is actually use autoencoders to like reconstruct the fact that you actually have this three-dimensional space. And then they fit SINDy to that three-dimensional space for Lorenz, and then you can like reconstruct back to the one-dimensional measurements. So that's something you would want to do, and we're thinking about it, thinking about adding it to the code. Jorge, or I'm not sure or is George or Jorge. There's also Kathleen Champion's paper from a couple years ago where they do something similar in that it's not that they assume that they only have access to some state variables, but they assume that there's they have the state variables, but they assume that there's some better latent space where they can either reduce the dimension or like have simpler models. And then again, they fit SINDy in that latent space of the autoencoder. So this is definitely an interesting place to go, and we're considering adding some of that to the code.
We got one more question in the chat. I'll go ahead and read it, then I'll let us move on here. And we got a thanks. So cool, answered that question just fine. Can you see Christina's question there, or do you want me to read it?
Yeah, no, I see it. Where driving parameters are not space and time, but something. So you're imagining you have some variable that's not a like it's not like q x of t. It's like, it's some function of environmental parameters rather than space and time. Is that the question?
Yeah. So if let's just assume you had experimental data where what's making this data change is some kind of outside parameter, and you want to figure out how is that outside parameter affecting your system. And it might be a collection of parameters. It might even be on different measurement scales. So it's even a challenging problem there to think, do you normalize these parameters, or how would this type of problem potentially work in this framework?
Yeah. The general answer is it's really hard. If you have let's say you have some spatiotemporal field and you have some external forcing inputs that maybe hopefully are slowly varying on some dynamical timescale. Discovering that is hard to do. You can build these SINDy models assuming some library of control inputs. So you can actually try and figure out the forcing that's being imposed on these systems. But generically, this is a really hard problem. One thing you can address if the forcing is on a slow timescale compared to the primary dynamics, you can sort of fit these SINDy models very quickly. So a lot of this stuff is like sub-second computations, and we're planning on putting this on GPUs and get it to like milliseconds. So if you have if it is varying on a slow timescale, you can recompute SINDy models like on a running time, and sort of rebuild your model as these parameters slowly vary in time. So that's one way you can address this drift. But yeah, generally this is really hard.
I think we could move on. Did you have more in your talk, don't you? Or was that it?
Oh no, that was it. I was told 20-ish minutes plus.
Hey, sweet.
I probably went over that.
Oh, then good. I thought we were just interrupting your talk with a bunch of questions here. Glad that we took ample time to dive into them then.
Yeah, well, thanks everyone for listening and for the great questions.
Yeah. I have sort of an orthogonal question, but I'll open the floor first to everyone on the call. Did anyone have any burning walk-on topics that they wanted to talk about? Just so I know that I'm not allocating time wrong. Give people just a second to maybe find their unmute buttons. No, well, someone interrupt me if you think of a walk-on topic here, but maybe I'll just ask one final question, and that might be the end of the Telecon. So Alan, I'm personally involved in some machine learning research to do anomaly detection with satellite data. Like my lab does a lot of data processing for just various NASA missions, satellites that we build. They send back the time series telemetry, and we try to make models of them and alert if something goes not normal. If we get data that significantly strays from the model. Is this kind of software kind of good for that kind of use case? Because I noticed at one point the Lorenz function, it kind of got off because there was a change point and it didn't like recognize that. Yeah, what are your thoughts there?
Yeah, it depends on the process. So yeah, one if it is a chaotic system, no, even if you like build the best model ever for it, there will still be some numerical error in your coefficients that will eventually give you a wrong lobe switch, if for instance for Lorenz. So yeah, it depends. If you're trying to use it for forecasting, I mean, no, even a perfect model will give you wrong things for chaotic systems at some point.
Can that forecast? Can it predict out into the future?
The models?
Yeah, what your stuff?
Oh yeah. I mean, once you have a SINDy model, you have a governing set of equations for the data. So
Oh
then you
yeah,
can
yeah.
just choose some new initial condition and evolve it. And my point is, even with Lorenz, even if your model is exactly right to computational numerical precision, you still will get lobe switches that are incorrect at some point. So this you have to be careful about forecasting. It depends what exactly you're doing for anomaly detection. If you're really just looking for like you're sort of tracking some data as it goes along, and suddenly there's a big spike or something, and you just want to like send alarm. It might be able to do something like that, where you sort of you build a model on some testing data without the anomalous behavior, and then when it sort of there's a big deviation between your model and data, you flag it. You say, okay, that maybe that's an anomaly. But
Makes sense.
yeah, I mean, there's a lot of different ways to do this. Yeah.
But then I guess if you didn't really know if there was an anomaly in your training data set or not, and you were just blindly throwing data at it, I guess you might like bake an anomaly into what it thinks is normal, and then
Yeah. So I mean that's interesting for a different reason. You might be able to like build a SINDy model that like actually models the anomalies, and that might tell you some physics things about it.
oh yeah,
But yeah, less helpful for anomaly detection. But actually, this is a general issue with anomaly detection. Even when you use like let's say you're doing anomaly detection in images with a neural network, somehow you have to train the neural network on like a clean data set, and you're like, oh crap, I have to figure out how to make a clean data set without anomalies first, and figure out how to distinguish.
totally. Cool, super interesting talk. I really like the machine learning packages that we're getting into PyHC. Obviously, that's an exciting area of exploration.
Awesome, thanks a lot.
And I will, let's see, I'll answer one question in chat, and then Jorge's got one more question here. Just a quick walk on topic of what was the final count for enrollment in the PyHC summer school. For those not monitoring the chat, we had around 500 people, actually over 500 people register for the PyHC summer school. Looking at the numbers here, I think we're about 40 people shy of 600 in registration. 108 of those are in person. The rest of them are virtual. So mostly virtual, but we have a lot of attendance in the PyHC summer school here. Kind of blew up. That's exciting. And thank you, Alan. You went ahead and answered the question in the chat. When we have these telecons, we're recording the telecons and we save them along with the chat. So for people interested in catching up on this or reviewing what questions were asked and answered, you can review that when we send out the email. Anything else, or do we want to go ahead and get 9 minutes of our day back? Going once, going twice. Cool, well, thanks everybody. I'm gonna go ahead and stop the recording here.